Okay. So testing. So for student and team, so can you see the slides I share? Can you hear my voice and see the slides I share? Student and I. Hello. Student and I, can you see the share?
Yes, Prof, can see.
Okay, good. So now let me start the recording. Good afternoon, ladies and gents. May I have your attention, please? So now it's a time for us to start our class. So first, let me make an announcement. So last week, you have attended the quiz 1, right? So I think every one of you have already get the results instantaneously. So if some of you would like to go through your quiz paper, so you need to send me an email so that I can ask OAS to retrieve your quiz paper so that I can help you go through. Because there are many questions, different of you get different questions. Of course, I cannot go through all the tutorial questions. I can just, go, individually according to your request. So that if some of you think you have not done very well, you want to go through, you want to review your quiz, you have to send me an email. Okay? So that I have to forward your email to OAS people, so that they will help me retrieve your quiz. Otherwise, without your request, I cannot even retrieve your quiz paper because I don't have the access. Only all the quiz and the examination are managed by OAS. So that upon your request, I can send your request and then to OAS, retrieve your quiz paper, and then we can schedule a time to to go through your paper. Okay, so just my email said, okay, I would like to go through my quiz paper. Could we schedule a time so that I forward your email to OAS, and then we can go through your quiz paper. Okay, so we have to do in this way. So for today, we are going to learn the second part, chapter 2 of electromagnetics, that is Gauss's law. Okay, so talking about Gauss, okay, so it's a German mathematician. Okay, one of the most famous or one of the greatest three mathematicians in human history. Okay, so not in the world, is in human history. One of the greatest three mathematicians in human history. So that is Archimedes, Gauss, and Newton. Okay, the greatest three mathematicians in human history. Gauss is also known as the Prince of Mathematics. Okay, Prince of Mathematics. So before talking about Gauss's law, so let me first, give you a brief introduction about this guy. So Gauss became even very well known when he was an undergraduate student. So the same as you. So at that time, so because we don't have any computer, so at that time people are so especially mathematicians, they are very interested in, for example, drawing different graphs with ruler and compass. Because, for example, how to use ruler and compass to draw, for example, a square or a rectangle or a literal triangle. Okay, so this is what you are interested in doing. Now we can, if I want to draw, for example, a circle or a literal triangle, you can just use computer program to do that. But at that time, computer have not been developed, so that people just use this ruler and the compass, okay, to draw different graph. Okay, so that at that time, so after one of the mathematical course, and then the professor, a very old professor, left 3 pieces of homework for the students to do, and Gauss quickly solved the first 2, but then he found the third one is very difficult, so that he spent the whole evening without any sleep, and then finally solved the third question. So the third question is how to draw this hypothetical with ruler and compass. So at that time, he found this is very difficult, spent the whole evening and solved the problem. So in the second day, attending the same mathematical course, the same professor, then he told the professor, said, okay, I must admit that I have not, learned your course very well, because you just left 3 questions for us. But I spent the whole evening to solve the third one, so I must not learn well. And then the professor was shocked. How he replied, Gauss, is impossible. Because actually I only have 2 pieces of homework going to do. The third one is my own project. I have a team with the other 2 PhD students. 3 of us haven't solved this problem within 1 year. And also intellectually, no one knows how can we draw this hypothetical with ruler and compass. How can you as an undergraduate can solve this difficult problem within 1 year? I just left the third question to you by mistake. This is a worldwide problem in that time. So because no one in the world knows. But Gauss just told the professor, said, okay, I solved this within 1 evening. This question, the professor and 2 of his PhD students haven't solved within a whole year. And then Gauss showed all his examples and the derivations and how he draw this hypothetical to the professor. And then the professor found, okay, was very shocked because he found Gauss' solution is really correct. So that even as an undergraduate student, Gauss became very famous. Because even as an undergraduate student, he solved a very difficult problem. At that time, no one in the world can solve. Of course, Gauss has many other great contributions to both physics and mathematics. So today, what we are going to learn is one of the most famous contributions of Gauss, which is Gauss's law. Okay, Gauss's law is one of the greatest law discovered in both physics and mathematics. So not only, for example, in electromagnetics, we use Gauss's law very often. Even in mathematics, Gauss's law has its own, so it is also widely used. So this is what we are going to learn. So for this chapter, actually was divided into these three sub-chapters. First, I have to introduce a new physical quantity that was called electrical flux. And then I will show how to calculate electric flux with Gauss's law, and then how to apply Gauss's law to calculate the electric field generated by these charged insulators. And finally, what's conducted in electrostatic equilibrium. Okay, so first, what are the electric flux? So in electric flux is defined. So last week we already learned two physical quantities. That is electric field and electric force. Okay, so this electric flux is a third quantity. So electric flux refers to the number of electric field lines penetrate through an interface, okay, a surface. So if I have a surface, the number of electric field lines passing through it is the electric flux. Okay, this is the physical definition. So mathematics electric flux is the inner product of E and A. E is the electric field, A is the surface vector. Okay, the surface vector, the surface vector is defined as the area, its magnitude is the area of the surface, and then its direction is the surface normal. Okay, so the inner product between two vectors we know, is equal to EA times cosine theta. So E here is the strength of the electric field, A here is the surface area, and then theta here is the angle between the surface normal and the electric field, and the surface normal and the electric field. Okay, so you can say when the electric field is perpendicular to my surface, which means the surface normal is exactly along the electric field, and then the electric flux is exactly equal to E times A. Electric field is equal to E, electric flux equal to E times A. But if the surface is inclined at a certain angle, we need to count this cosine theta. Or in other words, you can virtualize the electric flux as the electric field passing through the projecting surface that is perpendicular. The projecting surface of this A that is perpendicular to the direction of the electric field. Okay, so this is what we call the electric flux. Okay, so it's a number of electric field lines passing through this interface. So mathematically, it's equal to EA cosine theta. So you can say from this graph, the electric field lines passing through this inclined surface, which is given by this red, rectangle, okay, is exactly the same as the electric field lines passing through this green rectangle, okay. So it's the projection surface of the original rectangle along the direction perpendicular to the electric field. Okay, so that bear this question in mind. I would like every one of you, spend 1 minute to choose to take a look at this one. In which of the following schematics the electric flux through the surface A is zero? So I delivered this question on learning catalytics. Okay, with this session number, you can take a look. Okay. Yes, I already delivered there. So spend 1 minute to submit your answer. Okay, so thumbs up. Okay, So actually the right answer should be C, because I want the electric flux to be zero. Electric flux to be zero. So you know, in this case, both E and A is not zero. So if we want the electric flux to be zero, okay, we need this theta equal to 90 degree. Theta equal to 90 degree, which means the surface normal is perpendicular to my electric field lines. And the electric field lines has to be parallel to my surface. The electric field lines has to be parallel to my surface. So that we should choose C. We should choose C. Or you can directly see this problem through the definition of the electric flux. The number of field lines passing through the interface, okay, passing through the surface. So here you can see there are 9 electric field lines passing through the surface. So of course the flux is not zero. Here we have 6 field lines passing through the surface. So of course the field line is not zero. Only for this case, the field lines are exactly parallel to my interface. So the number of field lines passing through it is there. So that we should choose C. Okay? Any question? Good. So yes. So again, so here I would like to highlight 3 points for you. So first, this formula phi E equal to EA cosine theta is only valid for a flat surface. For flat surface, we have a well-defined A vector, okay, surface vector, because its surface normal only along a certain direction, okay? So this formula is only valid when I have a flat surface in a uniform electric field, okay? Flat surface in a uniform electric field, okay? Then, okay, of course, phi E is a scalar. Then if I have a non-uniform electric field or a curved surface under a uniform electric field, how can we do that? And then what we have to do mathematically is we need to divide the whole surface into infinitely small segments. For each small segment, we apply this E dot dA and then integrate this through the whole space, and then we can get the flux. Okay. So of course you can say this procedure. Of course, you can say this procedure is very complex. As I said, so in our course, we normally want to simplify the mathematical calculation for you. So in other words, I want you to show you some simple way to calculate the electric flux. So this is what we are going to show you in the following slides. Okay, so the Gauss law, as I said, is a very useful approach for us to simplify the calculation of the electric flux. So this is what we are going to talk about later. So first, before I talk about Gauss law, let's take a look at some tutorial question that is directly related with the electric flux. So first of all, tutorial question 1. Here I have a closed rectangular box. So with low charge enclosed inside in it, low charge enclosed in it. It rests within a horizontal electric field lines with the electric field strength given by this value. So I want you to calculate the electric flux first through this vertical surface, second through this slanted surface, and finally through the entire box. So part B, I told you I have a pyramid where the base is 6 meters square, and then the height of this pyramid is 4 meters. Okay, then it is placed in a region with a vertical electric field directed upwards, with a magnitude of 52 Newton per Coulomb. I want you to calculate the total electric flux through the pyramid's 4 slanted surface. Okay, so then let's take a look at part A one by one. So part 1 and part C want you to calculate the flux through this vertical and curved surface. Okay, vertical and curved surface. So that this is a closed rectangular box. Okay, so if you already attended this, watch the last video or in the Saturday lecture, so that we already learned that for a closed surface, the surface normal is always defined as a direction from inside to outside. Okay, from in to outside. So that's the first one. If we want to calculate the electric flux through this perpendicular surface, you first need to know what's the direction for the surface normal. Okay, as I said, surface normal is defined from in to out. So for this vertical surface, the surface normal should point to the negative x direction. Okay, because it's from in to out, always point to outer space. Okay, and then for this guy, slant surface, it point from in to out, then it should point on this direction to the top right direction. Okay. So that if you want to calculate the flux at this vertical surface, we first get its area. Its area is the product of the two edge lengths. Okay, 30 centimeters times 10 centimeters, we get this guy. This is area A, and then phi A should equal to EA cosine theta. E is given, A already calculated, and as I said, the surface normal is along negative x direction. It forms an angle 180 degrees with respect to the electric field. Clear? Right? The surface normal on the electric field forms that direction 180 degrees. Any question? Clear? How about student on 9? For this vertical surface, the surface normal and the electric field forms that direction 180 degrees. Because the electric field is along positive x direction, point to the right, and the surface normal is along negative x direction, point to the left. So that when you do the calculation, you find, okay, this guy is minus 2.34 kilonewton square per kilonewton square meter per coulomb. So for the slanted surface, we first calculate the surface area. So you can say this angle is 60 degrees. So which means my theta here is also 60 degrees. Okay, theta here should also 60 degrees. So the direction between surface normal and the electric field is also 60 degrees. Then we calculate the area A. Area A equal to this 30 centimeters times this edge length. Because this is a right angle, so that 10 divided by cosine 60 degrees, we can get the length here, so that we get A is about 0.06 square meter. Then we substitute A and E into the equation for electric flux, E times A times cosine theta. Okay, EA is already calculated, theta equal to 6 degrees, so that you can say we get phi A equal to positive this value. Okay, any question? Any question? Good. Now let's look at part 3. Part 3 wants you to calculate the electric flux through the entire box. So that for this triangle box, we have other, 3 surfaces. Okay, the front rectangular surface, the back rectangular surface, and the base. So can you directly tell me what's the electric flux through these 3 surfaces? How much is the electric flux through that 3 surfaces? The front and the back surface and the base. What are the electric flux through that 3 surfaces? Some surface. Sorry, could it be louder? 0. Yes, very good. Why is there? Because the electric flux are all parallel to these 3 interfaces. As I said, when the electric flux is parallel to the surface, so when the electric field is parallel to the surface, the flux is always there. Okay, the flux is always there. So the other 3 surfaces give you 0 flux. So that the net flux through the entire closed triangular box is equal to phi A prime plus phi A. You can say these two are just, the same in magnitude but different in sign, so that we get the net electric flux is 0. Okay, is 0. So actually, this is a very important conclusion. Okay, there are 2 important conclusions. So first, if we have a closed box, no net charge grid inside, the total electric flux is always 0. Actually, this is Gauss's law, which I will talk about that later. Another part is, okay, if you say, okay, this vertical surface is just a projection of this, slanted surface, okay, of this inclined slanted surface. So you can say their electric flux are the same in magnitude. So actually, this gives us another hint. If we have any shape of surface, either it's curved or inclined, as long as this surface is placed in a uniform electric field, then if you want to calculate the total flux through this curved surface, what we do is first to find the projection area of this curved surface perpendicular to the electric field, and then use the electric field times the projection surface area, we can get the total flux. This is the other conclusion we get from this example. So that we can use it to solve part B, for part B. Okay? So for part B, what we have here is a pyramid in this way, have a square base and 4 slanted surface. The question wants us to calculate what are the electric flux through the 4 slanted surface. So of course, this looks very difficult, right? So if you want to calculate the flux through each slanted surface, first you need to find out the area of the slanted surface and then the direction of the surface normal. And then repeat the procedure for this 4 surface, and then plus and together get the final results. Of course, this is a long way, but that will be very difficult. But now, if you apply what we learned from part A, first find the projection area of the 4 slanted surface perpendicular to the electric field. What is that? Okay, perpendicular to the electric field is actually the base. Then the projection surface of the 4 slanted surface is just the base. Okay. So what we say is a closed surface in a uniform electric field, the total electric flux will be there. So that we can quickly get my phi net equal to phi base plus phi 4 slanted surface should equal to 0. Right, this is what the conclusion we get from the first part. If we have any closed box put in a uniform electric field, the total electric flux is always there. So that if you apply this law, clearly my phi base plus phi 4 slanted surface should equal to 0. So that my phi 4 slanted surface should equal to minus phi base. In this case, you just need to calculate what is my phi base. Okay, my phi base. So the basement is very easy, okay? It has a square shape, so that A is 6 by 6 equal to 36 meters. Electric field directly upward. As I said, surface normal should directly always from inside to outside. So can you tell me what's the direction of the base? What's the direction of the surface normal of the base? Very good, to the point downward. So electric field upward, surface normal downward. So of course they form another 180 degree. So that electric field times 36 times cosine 180 degree, I can get the phi base. Then phi 4 slanted surface is minus phi base. Okay, problem solved. Clear? So if clear, I would like everyone of you try this question. I have just delivered on learning catalytics. Okay, on learning catalytics. Okay. So I will give you 3 minutes and try to submit your answer. So here I have a hemispherical surface, so which is half of a spherical surface. Its radius is 2 meters and located in a uniform electric field with a magnitude E equal to 20 volt per meter. Okay, this electric field is normal to its projection flat curved surface. Okay, I want you to calculate what's the magnitude of the electric flux through this hemisphere. What's the magnitude of the electric field through this hemisphere? So you just apply the what we learned from your part. Okay. So pay attention here. So for part 2, you can say I have any MCQs here, and this MCQ is very similar to your quiz 2. Okay, to your quiz 2. So that every one of you should pay attention to all the questions I deliver and ask you to do. Okay. All the additional questions I ask you to do. Okay, is help you to prepare your quiz. You may expect, some of this question will be tested in your quiz too. Okay, so time's up. Let's look at your okay, so time's up. Let's look at your answer. Okay, so here we should choose what we should do is, of course, the projection area of the surface is actually this this circle. So that the electric flux through this hemisphere should be exactly the same as the electric flux through this this circle. So that we just use E times pi r squared. Just use E times pi r squared to get the final results. Okay, E times pi r squared to get the final results. So that if you do the mathematics correctly, you should find okay the final result should be B. Should be B. Okay, B. So then the next part is Gauss's law. So to understand Gauss's law, we need to first understand what is the Gaussian surface. Gaussian surface is any closed surface in the space. So it can be a virtual surface or a real surface. As long as it's a closed surface, this is Gaussian surface. So then Gaussian law tells us, okay, the net electric flux through any closed surface or through any Gaussian surface is just proportional to the net charge enclosed by that surface. Enclosed by that surface. Okay, so mathematically, my find okay, so this is actually a closed form integration because of the computer problem, so that it cannot be displayed correctly. But do remember, this is a closed form integration. So which means if you want to calculate the total electric flux through any closed surface, you don't have to do this complex integration. You just have to count the net charge inside this closed box, this closed surface. And then summing them up together and then divided by epsilon naught, you can get the total electric flux. Total electric flux through this Gaussian surface. Okay, so this is what Gauss's law states. So take this as an example. Okay, so here I have 5 charges. 1, 2, 3 placed inside this, this Gaussian surface. 4 and 5 are placed outside. Then can you quickly tell me what should be the electric flux, enclosed by this closed surface? What should be my electric flux? Any idea? As I say, we just count the charge inside the box. So there are only 3 charges, 1, 2, and 3 are placed inside the box. So that then plus together is Q1 plus Q2 minus Q3, then divided by epsilon naught. That will give us the total electric flux through the surface. Clearly, you can see Q4 and Q5, they are outside the Gaussian surface. So which means although they contribute to the electric fields along the Gaussian surface, but they does not contribute to the net electric flux. They does not contribute to the net electric flux. So which means if Q1, Q2, and Q3, they are all equal to 0, we have Q4 and Q5 outside. So even the electric field at this Gaussian surface will not be 0, but the integration of them as a flux, okay, the integration of the flux will be 0, okay. So this is also what Gaussian law tells us. So in Gaussian law, there is 3 keywords, 3 keywords. So first, it's a net electric flux, not a local electric flux. It's a net electric flux through the whole surface. Okay, and then this surface has to be a closed one, not an open one. So for example, if I have a single surface or 2 surface, or 2, intersect surface, that cannot be considered as a closed surface. The closed surface must be a sphere, a cylinder, or a cube, something like that, okay, or a pyramid. It has to be a closed surface. And then finally, it's equal to the net charge inside, okay, net charge inside this box, okay, has to be the net charge. So Gauss solar actually has many applications. So first, it can help us to anticipate the total charge inside a certain area, As long as we can know the total electric flux through a closed box, we will be able to estimate or not estimate, actually to rigorously calculate what are the total charge contained inside this box. Okay, so this is our actual question 2. So here we have a tube. We have a tube, a closed surface with dimension. This A equal to this B equal to 0.4 meters. And this C height is 0.6 meters. Is located in an electric field which is directly along x direction. Okay, it's always the electric field always along x direction. Its magnitude is increased with x as 3 plus 2x squared. So I want you to calculate first the net electric flux through the whole closed surface. And then I want to ask you what's the net charge enclosed by this surface. What's the net charge enclosed by this surface? Okay? So first, look at this closed surface. This is a tube, okay? So it contains 6 surfaces. Could you know the electric field here is directly along x direction, Then could you quickly tell me what are the electric flux through the left, right, top, and bottom surfaces? What are the electric flux through the left, right, top, and bottom surfaces? So student and team, could you type your answer on the chat room? So what do you think? Yes, very good. It should be 0. Why? Is because the electric field are parallel to all these 4 surfaces. Okay, left, right, top, and bottom. Electric field are all parallel to these 4 surfaces. Once the electric field is parallel to the surface, then the electric flux to the surface should be 0. So which means now the net electric flux is only the summation of the front and the back surface. Okay, the back surface is located at x equal to a. Okay, so this is x equal to 0. This is located at x equal to a. This surface is located at x equal to a plus c. Okay, this surface is located at x equal to a plus c. Okay. So that what we do is just calculate the total electric flux at x equal to a and x equal to a plus c. Plus them together, we can solve this question. Okay, plus them together, we can solve this question. Okay, so that we use E times A at x equal to a and A at x equal to c. So you know the electric field is actually different at different x, but if x are the same, and then the electric field is uniform. So that at x equal to a, the electric field just equal to 3 plus 2a squared. At x equal to a plus c, the electric field equal to 3 plus 2a plus c squared. Okay, so that this 3 plus a squared are the electric field at x equal to a. 3 plus a 2 plus ac squared, that is electric field at x equal to a plus c. So the area is always a times b. Okay, area is always a times b. How about the direction? So look, the direction, as I said, should always directly from inside to outside. This is a very important rule you have to follow. Okay, so that for the back surface, the surface normal is actually this blue arrows. Okay, it should directly along negative x direction. so that it forms an angle 180 degree with respect to the electric field. So that once we multiply the electric field and the surface area together, we need to times another cosine 180 degree. At the front surface, the surface normal and the electric field are along the same direction, so that we just times cosine 0. So once you plus all the things together, you can get, okay, the final answer is 2abc times 2a plus c. So it's about 0.269 Newton square meter per coulomb. Okay, Newton square meter per coulomb. So the final part is I want you to calculate what are the total charge enclosed by this tube. Okay, enclosed by this tube. So what we do is apply Gauss's law. The total electric flux equal to Q in divided by epsilon naught. So once we know the total electric flux times this guy by epsilon naught, we can get the total charge. So the total charge is about 2.38 micron coulomb. Okay. Any question? Any question? Okay, so if no question, let's look at this one. Let's look at this one. Okay, this is another question asked about, 1 year ago. So it's more or less the same as that tutorial. So here we have a cube. Now it's a cube of dimension 1 meters, as shown in this figure. So the edge length is 1. Then I have an electric field which is non-uniform through the space is given by 2 plus 5y. So you can say its strength changes at different y coordinate, okay? But if y are the same, then the electric field is a constant, okay? So it's always directly along the y direction. I want you to determine the net electric flux through the entire box and the net electric charge enclosed by this tube, okay? Enclosed by this tube. So these are the same. My electric field is directly along y direction, so which means the electric flux through the top, bottom, front, and the back surface are there, right? Because y is parallel to the top, bottom, front, and the right surface. So if we want to calculate the total electric flux, we just consider the electric field at the left and the right interface. The left interface located at y equal to how much? Left interface located at y equal to how much? Any idea? Left surface located at y equal to how much? Very good. Located at y equal to 0. How about the right one? Y equal to how much? The right surface located at y equal to how much? Very good, 1. So that you can quickly get the electric field at the left and right surface. At the left surface, y equal to 0. Okay, so it's 6. Right surface, y equal to 1, so it's 11. So this is the case. The electric field at the top, bottom, front, and back surface 0. We only consider the electric field through the left and the right surfaces. So that we assume at the right is phi A, at the left is phi B. So that for the left surface, because located at y equal to 0, so that we have 6 plus 5, 0 is 6. Times the area is 1. Y is 100 cosine 80 is because for left surface, the surface normal directly along left direction. Okay, so it's anti-parallel to my electric field, 180. The right surface is directly to the right, so that is 0 degree. We have cosine 0. So that when you substitute all the number into this equation, you can get the net electric flux equal to 5. Okay, and then apply Gauss's law. The second part. The net charge should equal to epsilon naught times my phi net. So it's about 44 micron coulomb. Okay, 44 micron coulomb. Okay, any question? So if no question, let's consider this example. I just deliver this question on learning catalytics. Okay, so try to take a look and submit your answer. Okay. So here I have an electric field E equal to 8I plus 2yj. So x direction is the electric field is 8, y direction is 2y. Okay. What is the magnitude of the electric flux through the top surface? Okay. I want you to calculate the magnitude of the electric flux through the top surface. One last minute. Okay, so thumbs up. Let's look at okay, so what we are looking at is the electric field at the top surface. So first we need to find out the electric field there. Okay, in order to get the electric flux, we need to find the electric field there. Can you tell me the top surface is located at y equal to how much? Very good. Should be y equal to, the top surface should be located at y equal to 4. Okay, y equal to 4, not y equal to 2. Okay, the top surface, because this is 4, so it's located at y equal to 4. So that if you substitute y equal to 4 inside, you get, okay, the electric field there is unity. H I plus j. Both x and y component are 4, or are 8. Both x and y component. Then the top surface. The top surface, as I said, the electric field, the surface normal should direct from inside to outside. So surface normal should be along the top, right? Point to the top is along positive y direction. Positive y direction is actually j. Okay, area is 4 by 4 equal to 16. 16. Okay, so along positive y direction, which is j. This is A. And then, as I said, the flux equal to the inner product between A times J. So in this case, we don't need to find the angle. We just, apply the inner product. I times J equal to 0, J times J equal to 1, so that we get 128 Newton square meter per coulomb. Okay? So we choose D. So this is part 3. The question 3. For question 3, I have a point charge placed at the center of a cube of length L. What's the total electric flux through the whole surface of the cube? Then what's the total flux through each surface of the cube? Then say, would your answer to part A and B change if the charge is no longer located at the center of the cube, but slightly shifted from the center? Okay, so let's look at A, B, C one by one. So I would say this question is actually quite easy. It's quite easy because we only have so the cube is a closed box, right? So if we want to calculate the total electric flux through any closed box, we just count the charge inside it divided by epsilon. That is the answer. So that is here my phi cube equal to epsilon divided by q divided by epsilon naught, which is actually q divided by epsilon naught. So which is actually the capital Q divided by epsilon naught, the cube. Then I want you to calculate what are the electric flux through each surface. When this is a cube, when the point charge is located at the center, so that each surface will see the charge. So the charge will have the same distance to each surface, right? Because of the symmetry. Due to the symmetry, each surface or each face of the cube will see the charge at the same distance. So that we can quickly tell that, okay, the electric flux through these 6 interfaces should be the same. So the net electric flux is actually equal to 6 times. So which means the net electric flux is the summation of the electric flux through each phase. Because the flux through each phase are the same, we can get the net electric flux equal to 6 times the phase. So which equal to Q divided by epsilon naught. So that my phi phase should be 6 divided Q divided by 6 epsilon naught. Okay? Any question? Then for part C, the part C says, okay, my charge is no longer located at the center, but slightly shift from the center, but still within the cube. So then according to Gauss's law, right, the total charge inside the box will be unchanged, still Q divided by epsilon naught. But bear in mind, in this case, because we no longer have such symmetry, okay, so that the charge no longer form the same distance to each phase. So which means now each phase will feel different flux. Although all this flux plus together still Q divided by epsilon naught. But we can no longer assume, we can no longer say the flux through each surface are the same. So that through each surface, my phi phase is no longer Q divided by 6 volts. Although the total charge remains unchanged, remains 6 divided by epsilon naught. The flux through each phase will change. Okay, so this is how you should answer this question. Okay. Now the last one. Okay. So the Gaussian law, apart from can help us to determine how many electric charge are located within a certain closed surface. It can also help us to calculate the electric field due to some symmetric charge distribution. So what we learned from our last week, if I have electric charge distributed, for example, across a spherical or spherical surface, what we do to calculate electric field is we use to apply Fuller's law for each small segment, integrate together to get the total field. But the integration is normally very complex. But if we use Gauss's law, we can greatly simplify that calculation. So how can we do that? So for example, here, if we have a charge Q uniformly spread of a solid sphere, what are the total electric flux through it? So that in order to get the electric flux through this uniform charge distribution, what we should do is first apply the symmetry of the whole system. Because of the spherical symmetry. So if we draw a Gaussian sphere, this dashed line is my Gaussian sphere, okay, Gaussian surface. Its center is exactly the same as the center of this insulating sphere, of this charge, okay? This charge is spread over the whole insulating sphere. Then, due to the spherical symmetry, we can see the electric fields everywhere along this dashed Gaussian sphere are the same, right? Because the charge is spread over a spherical symmetry, object. So that my electric field should also have this spherical symmetry. So that is all everywhere the same. So that if you want to calculate the electric flux, okay, the total electric flux is just equal to the electric field times the area of this Gaussian sphere, right? Because the electric field is everywhere the same, is a constant. We can put it out of the integration. The closed integration of dA is just the surface of the sphere, which is 4 pi r squared. So 4 pi r squared. So here we just divided by mathematics. And this E times 4 pi r squared should, according to Gauss's law, equal to the total charge within my Gaussian sphere, which is Q divided by epsilon naught, which is Q divided by epsilon naught. So that, I just put this 4 pi r squared to the denominator of 4 divided by epsilon naught. I can quickly show my E equal to KEQ divided by r squared. So you can say this is exactly Coulomb's formula. This is exactly Coulomb's formula. So that actually, what this example tells us that if we have a charge uniformly spread across a whole sphere, then outside the sphere, the electric field is exactly the same as a point charge located at the center of the sphere. Okay, so outside the charge, you cannot tell, or the difference between this and this configuration, because the electric field outside this sphere are exactly the same as the electric field of a point charge. Okay, so this is one important conclusion we can get. But if you do the integration of the charge over the whole sphere, you will get the same results. But of course, that will be very complex. So Newton spent about 20 years in order to integrate the gravitational field generated by a sphere. He spent 20 years, barely published his results. Because at that time, he does not have access to Gaussian law. Gaussian is after Newton. Okay, he does not have access to Gaussian law. Okay, but now with Gaussian law, actually we can solve this problem, prove this, just within 5 minutes. Okay, within 5 minutes. So this is why Gaussian law is very, very powerful. So the second example, if we have, for example, electric field uniformly distributed across a line, and then the way of us to calculate Gaussian sphere is to, develop a cylinder, a cylindrical Gaussian surface. So for this cylindrical Gaussian surface, because of the, rotational symmetry, the cylindrical symmetry, we can tell that the electric field everywhere along this cylindrical surface should be the same. So that if you integrate the electric field along the cylindrical surface, what we should get is E times 2 pi RL. 2 pi RL is the surface area of the cylindrical surface. So according to Gaussian law, this guy should equal to Q divided by epsilon naught. And then rearrange this equation, you can quickly get my E equal to lambda divided by 2 pi R epsilon naught, because Q divided by L is the line charge density lambda. Okay, so this is also exactly the same as the for tutorial 5. So you remember last week tutorial 5 asked you to calculate the electric field if an infinitely long charge distribution. We have to do a very complex integration. Okay, but now if you just solve, you can still solve this within less than 5 minutes without doing any integration. Okay. So of course you can apply Gaussian law to this, surface, to this surface charge. So all these examples are in your lecture notes in the last video, so that I will not talk about this in detail. If you correctly construct the Gaussian surface, you can show, in this case, the uniform charge distributed across the surface. Okay, it will just generate a uniform electric field, which is sigma divided by 2 epsilon naught. Okay, which is sigma divided by 2 epsilon naught. Okay, so that if you want to know detail why it's given by this equation, you refer to your notes. I just do a summary here. So now, my last example I would like you to try is this one. Here I have a material in a uniform charge density. Okay, a uniform charge density filled in the cube. And the dimension of the cube, each side is 8 centimeters. I want you to calculate the total electric flux through the whole cube. I just, deliver this question underneath catalytics. You try to take a look. Okay, time's up. Let's look at the solution. Okay, so what we should do to calculate the total electric flux, because we want to know the total electric flux through this cube. Cube is a closed surface, so that we just use epsilon naught divided by Q divided by epsilon naught. So Q should equal to the volume charge density times the volume. So here I give you the volume charge density is 38, okay, nanocoulomb per cubic meter, okay. I use this rho times the volume, okay. The volume is 8 centimeters equal to 8 times 10 to the minus 3. Its cube is the volume. So that you times all this together divided by epsilon naught, you will get about 2.2 newtons per meter per coulomb. Okay, so here we should choose C. We should choose C. So maybe in your quiz you should expect similar question, but just with a change of a number. Okay. So here I have another example, test 3 about 4 years ago. So that this question is not required, but I think this is a good example about how you should apply Gauss's law. So that I still provided in my, for example, tutorial material. But here I don't have time to go through it. So I would suggest after the class, every one of you try to take a look at this question and then compare with my solution. I show here. Okay, so here I will not talk about the solution, but I have already provide my solution here. So the last example is the conductor in electrostatic equilibrium. Conductor in electrostatic equilibrium. So first you have to understand what are the conductor in electrostatic equilibrium. So conductor in electrostatic equilibrium refers to a conductor. Once we put a conductor in the electric field, when there is no current flow or no charge, there is no current flow or no net charge motion on or inside this conductor. We call this conductor in its electrostatic equilibrium. So this is the definition. But what we have to bear in mind for conductor in electrostatic equilibrium is the following 3 points. Once a conductor is in the electrostatic equilibrium, the total electric field inside the conductor should always be there. Okay, first, the total electric field inside the conductor is there. Second one, the total charge inside the conductor is also there. Okay, so point 1 about the total field. Second part is about the total charge. Both the charge and the electric field are there inside the conductor. Okay. The last important property is how the charge and then the electric field at the surface. Okay. So part 2 tells us, okay, the total electric charge inside the conductor is there, but does not tell us what happens at the surface. Okay. So of course, if there is any charge on the conductor, that charge must all located on the surface. It cannot be located inside the conductor. It can all be located on the surface. Okay, all located on the surface. Then it should be located on the surface in such a way so that the electric field generated by this surface charge is always perpendicular. To the surface. Okay, is always perpendicular to the surface. Electric field and any conductor should be perpendicular to the surface. You can say everywhere perpendicular. And the magnitude of the field is just the epsilon divided by sigma divided by epsilon naught. Okay, sigma here is just the surface charge density. It's just the surface charge density. Surface charge density divided by epsilon naught is the electric field. Okay. So then the last important example I would tell, so this is a summary I told you. I summarized here because it was tested quite often in the quiz and also in the final examinations. So that the 3 properties are always related with a solid conductor. But in your quiz or final examinations, okay, even in our tutorial, so people are very interested in if we create a hole or a cavity inside the conductor, then we put some charge inside the cavity. So we cannot put charge inside the conductor, but then we can make the conductor to be hollow. Once it's hollow, we can put the charge in the hollow cavity, and then this can cause the charge to to be distributed on the inner and outer surface of the conductor. Then people are interested in knowing, then if we create a hole to the conductor to make it hollow, then we locate some certain charge in this hollow area. What will charge distributed on the inner and outer surface? These are very often tested in the quiz on parity relations. Okay, so here I just make a summary for you. If you want to calculate, you always apply the rule here. So I just have two formulas for this guy. The first one, the surface, the charge on the inner surface is always minus the charge of the cavity. So I will show why later. But here I just make a summary. You remember, okay? Remember this one. Apply that in your quiz on parity relation. You can create a similar hole. So as I said, the charge on the inner surface here is always equal to minus the charge we put inside this hollow area. So this hollow area I put because I say this is a cavity. So the hollow area I say the total charge inside is Q cavity. So my Q in at the inner surface always equal to minus Q cavity. Okay. Then how about the charge at the outer surface? The charge at the outer surface. If the outer surface is grounded, okay, if the whole conductor is grounded, and then the charge at the outer surface is always there. Then, if the charge is not grounded, but the question tells us, okay, in this case, the total charge on the conductor is Q. So what is the total charge? Total charge, which means the charge of the inner and outer surface plus the energy. Okay, that is the total charge or net charge. And then because, as I said, no matter how many charges we put on the conductor, the inner surface is always minus Q cavity. So in order to make the Q cavity, the net charge to be this Q net, and at the outer surface, the charge should be Q cavity plus Q net. Okay, Q cavity plus Q net. So in this case, you can say Q out plus Q in. This Q cavity cancel out together, we get Q net. Okay. So if the question tells us, okay, I put a certain charge in the hollow area of the conductor, I also put a certain charge on the whole conductor. You should be very in mind. In this case, the charge will distribute in such a way at the inner surface, my Q is always minus Q cavity. Outer surface is Q net, the total charge of the conductor, plus the charge inside the cavity. Okay? Bear this, two formulas in mind, and then you can quickly save your time to solve the question. Okay? Now let's look at tutorial question 4. So here I have a solid insulating sphere of radius A. It has so this is an insulating sphere A, okay? It has a volume charge density equal to rho and a total charge capital Q. Concentrated with this solid insulating sphere is uncharged, okay? Uncharged, which means is total charge is zero. You say any conductor is uncharged or charge neutral. That means the total charge is zero. Total charge is zero. Just means my Q net is zero. Does not necessarily mean Q in or Q out is zero. Okay, it just means Q in plus Q out is zero. That is charge neutral. Okay, charge neutral is total charge. But I can still have charge distribution on the inner and outer surface. Just this two plus together should cancel each other. Okay, so then this question tells us, okay, this has a total inside the cavity. I have a total charge Q here. Consider with the charge neutral conductor. I want you to calculate what's the charge on the inner and outer surface. Therefore, what's the charge density on the inner and outer surface? Then I want you to find out the electric field in the 5 regions. Okay, A smaller than so R smaller than A, which is in the conductor, between the insulating and the conductor, inside the conductor and outside the conductor. Okay, so let's take this one by one. So first, first I want to show why at the inner surface, the charge should always be minus the charge inside the cavity. Is it because we know inside the conductor, the electric field is everywhere equal to zero? Okay, the electric field is everywhere equal to zero. Then if we create a Gaussian sphere inside the conductor in this way, Okay, in this way, you can quickly show that because the electric field is zero, the total electric flux is also zero, right? If the total electric flux is zero, according to Gauss's law, the total charge enclosed by the Gaussian sphere should be zero. You can say the total charge inside this red Gaussian sphere is just my Q1 plus Q, so that I can directly say my Q1 equal to minus Q cavity, okay, minus Q in this case. So if Q1 equal to minus Q, and then my sigma should equal to Q1 divided by the area. So the area of this sphere inner surface is 4 pi b squared, 4 pi b squared. So that we get my sigma 1 is minus Q divided by 4 pi b squared. Okay? So now for part 2, charge neutron, as I say, charge neutron is Q1 plus Q2 equal to 0. So in this case, my Q2 should be minus Q1, so it's exactly equal to the Q cavity. Okay? So this also agreeing with what I show here. If my Q net is 0, my Q out should always equal to Q cavity. Okay? Q out should always equal to Q cavity. This is exactly the same. So that my sigma 2 equal to Q divided by 4 pi c squared. That is the surface charge on the outer surface. That's the surface charge on the outer surface. Okay, so any question here? Any question? Any question? So no question, let's continue to the second part, okay, the last part. The last part, what we want to do is to calculate the electric field in these 4 regions, okay? So that we apply Gauss's law, because that's when we construct the Gaussian sphere in this way, because of the spherical symmetry, we can tell the electric field is uniform, everywhere the same. So that we just put it outside the integration, so that it becomes integrated over a spherical surface. A, then it's just 4 pi r squared. So that my E just equal to Q in divided by 4 pi r squared. So in order to calculate the electric field in the 4 regions, we just need to calculate what is the total charge Q in these 4 regions. Then if my R is smaller than this radius A, radius A, and then the Q inside my Gaussian sphere is just a part of this capital Q. It's not all capital Q, just a part of this capital Q. So that we should calculate it in this way, that the volume charge density times the area. The area of the Gaussian sphere is just 4 divided by 3 pi r cube, okay? Then you substitute rho in equal to 4, Q in equal to rho 4 divided by 3 pi r cube into this formula. You can get my E equal to rho r divided by 3 epsilon naught. Rho r divided by 3 epsilon naught. So if my radius is between A and B, so it's just this Gaussian sphere. You can say for this Gaussian sphere, the charge enclosed by this Gaussian sphere is just equal to this capital Q, so that you get E equal to Q divided by 4 pi r squared epsilon naught. So how about if my radius is between B and C? What should be my electric field? The region B and C, what should be my electric field in this case? Then, if my Gaussian sphere is put in this way, what is the total charge enclosed by the Gaussian sphere? Remember, inside here I have capital Q, inner surface Q1, outer surface Q2. If my Gaussian sphere is placed here, what should be the total charge? What should be the total charge? Any idea? If my Gaussian sphere is not, if my R is within A and B, then the total charge should be now Q1 plus Q, right? Q1 equal to minus Q, of course, should be 0, so that my QE is 0. Any question? Give me some response. Yeah, I think in the future you need to spend some time. If you don't have time to, for example, solve the question is okay, but you have to spend some time to understand what this question is asking for. Yes, any question here? Any question here? Then thirdly, if my R is larger than C, then what should be the total charge? If my R is larger than C, what's the total charge? R larger than C. Sorry? Yes, very good. It should be Q1 plus Q2 plus Q. So finally is a capital Q. So that again, outside I get KQ divided by R squared. Okay? Any question? Okay, so low question, let's consider tutorial question 5. So here I have a long straight wire surrounded by a hollow cylinder. Okay, this is a long straight wire with a charge lambda surrounded by a hollow cylinder. Okay, I know the hollow cylinder total charge on the hollow cylinder is 2 lambda. So which means my lambda in plus lambda out should equal to my 2 lambda. Okay, my lambda in plus lambda out. Okay, it says okay, the wire, this hollow wire. Okay, this hollow wire has a total charge equal to 2 lambda, equal to, which means my lambda in plus lambda out equal to 2 lambda. Then I want you to determine what is the charge per unit length on the inner and outer surface. Okay, this lambda in is just the charge per length. Okay, lambda times L is the total charge, but you can just consider this as a charge. Okay, on the inner and outer surface. And then what are the electric field outside the whole cylinder? What are the electric field outside the whole cylinder? And then what are the electric field just on the surface? Whether this electric field is equal to epsilon sigma divided by epsilon naught. This question, one by one. So this is the configuration. Here, in the cavity, I located a charge lambda inside it. Okay, inside it. I know the total charge on this wire on this cylindrical surface is 2 lambda. So that is Q net. So as I said, for the charge on the inner surface is always minus Q cavity. In this case, like Q cavity is a charge located inside the cylinder, which is lambda. So that you can quickly get my Q in should equal to minus lambda. As I said, Q in always equal to minus Q cavity. Here lambda is my Q cavity. My outer surface is always equal to lambda net plus lambda cavity. Okay, lambda is this Q cavity. Then Q net is 2 lambda. So which now means my Q out equal to 2 lambda minus Q in. Okay, because my lambda in plus lambda out equal to 2 lambda total charge. Okay, so this is equal to 2 lambda plus lambda equal to 3 lambda. Okay, then problem solved for part 1. You directly apply my summary. The formula given in the summary, you can get the final answer. Okay, for part 1. So then part B, what we do is I want you to calculate the electric field outside this cylinder. Outside this cylinder. So you can say, now if we construct this green Gaussian sphere or Gaussian surface in this way, can you tell me what is the total charge located inside this Gaussian cylinder? What are the total charge? It should be lambda plus lambda in plus lambda out, right? Right? Lambda plus lambda in plus lambda out. So that's the total charge should be lambda in. So of course E times 2 pi RL. So this is the electric flux. Because the electric field is everywhere the same, integral of dA across a cylinder is just equal to the surface of the cylinder, which is 2 pi RL. So as I said, the charge enclosed by my Gaussian cylinder is the total charge lambda plus lambda in plus lambda out. Lambda in plus lambda out equal to 2 lambda. So that in total I have 3 lambda here. 3 lambda divided by epsilon naught, that is Q divided by epsilon naught. So compare these two formula. This L cancel out each other. You can directly get my E equal to 3 lambda divided by 2 pi epsilon naught R. So part B also solved. So part C is want you to determine whether this formula, when it's located at the inner surface, is equal to sigma divided by epsilon naught. So you know, lambda is a line charge density, sigma is a surface charge density. Okay, just at the outer surface, I have 3 lambda divided by 2 pi a epsilon naught. Then I have to show whether this is equal to sigma divided by epsilon naught. So that we first need to find out what is a surface charge density, sigma. Surface charge density means what? Is the sigma times the surface area should equal to the total charge. Lambda is a line charge density. Line charge density means what? I use lambda times L, that will give us a total charge. So which means the surface charge density should be equal to, for example, at the outer total charge equal to 3 lambda times L. So this is because at the outer surface, the non-charge density is 3 lambda. 3 lambda times L is the total charge. Total charge divided by surface area, 2 pi a L, that is the surface area. So this L cancel out each other. You can see the 3 lambda divided by 2 pi a. So the circle of the outer surface, the circum of the outer surface, that will give us a surface charge density. So that if you calculate the surface charge density in this way, sigma divided by epsilon naught just equal to what we calculated. Okay, just equal to what we calculated. So this is how you show actually the at the outer side of the cylinder, this electric field is just equal to sigma divided by epsilon naught. Okay. So then I will submit the last question to go through a tutorial question that was tested 3 years ago. Okay, tested 3 years ago. So here I have a solid conducting sphere of radius 2 centimeter with a total charge minus 10 micron coulomb. Concentrated with this sphere, I have a conducting spherical shell with an inner radius 4, outer radius 6 centimeters, but a total charge equal to 5 micrometer. I want you to determine the net charge enclosed by a concentric spherical Gaussian surface when the radius of the Gaussian sphere is 1357 centimeters. And then what are the electric field at a distance 6 centimeters away from the center of the conducting sphere? Okay, so this is actually the configuration we are looking at. This is the configuration we are looking at. Okay, conducting sphere and then a hollow spherical sphere. Okay. So first, of course, in order to calculate what are the Gaussian total charge within a certain Gaussian sphere, we need to know what are the charge on the inner and the outer surface. So you can say the question tells us, okay, on the conducting sphere, I have minus 10 micron coulomb. Then if you apply my formula, the inner surface always into minus the cavity. You can quickly tell at the inner surface, the total charge is 10 micron coulomb, okay? Because it's minus inside. Then how about at the outer surface? How about at the outer surface? The outer surface Q should be Q in plus Q out should equal to the Q net. So the outer surface should be Q net plus Q cavity. Okay, outer surface should be Q net plus Q cavity. Q net is 5 micron coulomb. Q cavity is minus 5 micron coulomb. So that at the outer surface, I should have minus 5 micron coulomb. Okay. So this is how you get that at the inner, because inside I have minus 10. So at the inner surface, I should have positive 10. So outer surface plus inner surface should be equal to the total charge 5. So that at the outer surface, I have minus 5 micron coulomb. So in this case, I have determined both the electric charge on the inner and the outer surface. Then we will be able to calculate the total electric charge. Okay, remember the charge distribution. At the sphere minus 10, inner surface 10, outer surface minus 5. Then for Gaussian surface just inside this sphere, as I said, low charge can be placed inside the sphere, so that the net charge should be there. Then if I place my Gaussian sphere here, what are the total charge inside by my Gaussian sphere? If I put my total charge here, Gaussian sphere here, the total charge of course only includes this minus 10, right? Then how about if I place my Gaussian sphere, between 6 and 4 here? Yes, very good. That should be 10 minus plus 10 minus 10. That should be there. So at the outer surface, I should plus all this together, 10 minus 10, 10 and minus 5. So that will give us total minus 5. Okay, total minus 5. So the last question is quite easy. So I want you to calculate the electric field, at this Gaussian sphere. So that you just construct the Gaussian, the Gaussian law. The Gaussian law So that E dot dA integrate over this whole sphere because of the spherical symmetry is just equal to E times the area of this sphere, which is 4 pi r squared. R is equal to this 7 centimeters. So QE we already get is just minus 10 plus 10 plus minus 5. So that it should be minus 5. So that when you inject all the value into this equation, you can get E is minus 9.17 times 10 to the 6 Newton per Coulomb. So the magnitude is this guy. Minus means my electric field should point from infinity back to the center of the sphere. Okay. So that if you have any question, I will still be here for half an hour to do the consultation. So otherwise, the class can be dismissed. So do remember this Friday afternoon, we still have this consultation session. If you want me to help you go through your quiz, do remember to send me an email so that I can retrieve your quiz paper in advance from all this. Okay? So if no questions, so that's all for today. Okay. So first, any question for student online? Any question for student on team? Yes.
That's right. What is it that the Q out, right? In this case, because the charge, the cavity charge is offset.
Yes.
But can I ask why the outside right, is
uniform? Yes. This is because the inner charge and the outer charge, the inner charge and the no matter it's symmetric and asymmetric, the inner surface charge will always try to cancel out the electric field generated by the charge inside.
Okay.
Okay. So which means the electric field due to the charge at the inner surface and this point charge should be zero. Should always be there.
Okay.
On the outside, at the outer surface, the electric field are all due to the charge on the outer surface.
Q out.
Yeah, the Q out. So do remember the electric field must be everywhere perpendicular to the surface.
Okay.
Only when the field is uniformly distributed, the electric field will be everywhere perpendicular to the interface. Otherwise, it cannot be perpendicular to the interface.
Okay.
Okay.
So for example, if I have, if let's say the charge makes a field, if the charge makes a field like this, then
the inner surface will make a charge. The inner surface, the total charge will make a field in this way. It will always cancel out the electric field everywhere. So that which means outside this cavity, the inner surface electric field will exactly cancel out the field of the point charge.
The inner surface, the electric field is. Can you draw it out? Like,
so the
how is it?
For example, let me this one.
You have to erase it.
Yeah. Yes. You have to do this one. So, for example, for this charge, the electric field is actually okay. The electric field is everywhere like this, right?
Yeah.
Then for the inner surface, it will just generate the electric field in the opposite way.
Okay.
For example, that it will generate for example,
different colors.
Yeah, for example, the inner charge will just generate a point this way and this way. It will completely cancel out the electric field of the charge. Okay. So maybe it's not erase all this. I should put it this way. So that for this charge, at this position, it sorry.
Okay.
So at this position, it generates electric field in this way. this position in this way, this position in this way, because it should point from the charge out. And this in this way, and then the inner surface at this position, it generates the electric field in a exactly opposite way. It cancels out the electric field everywhere.
So the inner surface is the electric field from here, like that, is it?
No, the inner surface will form, and the inner surface, the inner surface will form electric field everywhere.
Okay.
It will just cancel out the electric field, just outside this conductor. Otherwise, the electric field here cannot be there.
Okay, okay. The inner surface charge, the electric field from in the inner surface, right, is it from here pointing to the negative side?
No. It's from the electric field for the inner surface is actually from everywhere.
Everywhere.
Outside and inside both have the electric field.
Okay, okay.
Just outside the inner surface, the electric field of the inner surface and the charge completely cancel out each other.
Okay.
Inside they doesn't.
Okay.
Outside they completely cancel out each other. So
outside
which
is like this, like outside here, outside the conductor.
yes, that's right. Outside the conductor. So which means which means so what the inner surface you can visualize this way. If you put an electric field here, so if we don't have a conductor, you can know how the electric field of this point charge it is.
Yeah,
right?
exactly. Just goes.
Yeah, just goes out. If you have a conductor here, the inner surface will generate an electric field just as if you put a negative charge at the same position.
Oh, okay.
You as if it just point out a negative charge at the same position.
Okay.
So outside the cylinder, of course, it will cancel out exactly the electric field.
Okay.
Because the total charge, one point outward, 1 point back to the charge with the same magnitude, the field completely cancel out each other.
I see.
This is what the field generated by the inner surface piece.
Okay. So the uniform field outside is like from the Q out, right?
Yeah, the uniform field outside is just from the Q out, because the inner and the outer surface completely cancel out each other. It does not contribute to any field outside.
Okay.
And then the Q out has to be uniformly distributed. Of course, the charge has also to be uniformly distributed.
So these two fields are different. They are not.
Yeah, they are not the same.
I
They are
see.
not the same.
Can.
No problem.
Okay, can. Thank you, Prof.
Okay, no problem. So,
Yes. They got one question on finding the critical angle in the diamond for TIR. They only give you an angle.
Sorry, it doesn't know what?
Total internal refraction.
Yes.
In diamond.
Okay.
But they only give you one angle. Then they don't give you any refractive index. Then how you supposed to find?
From that, so could you, for example, draw a certain bit of diagram, because I'm not sure what kind, because I am not
They don't
involved.
have diagram. It's just words.
Sorry.
So they give you. Let me write down.
Your quiz. Because I have not been involved in the quiz setting for quiz one. I'm in the.
They give you incident angle of 67.8. Then they tell you it's a diamond. So diamond. Then that's it. They ask you to find the critical angle.
They give you what? This is the incident angle.
But they never give you the refractive index. Then how are you supposed to find?
So what is this angle? I think this should be this cannot be the question. What does this question state? What is this angle?
The incident angle. They wrote an incident angle of 67.8 degrees. Then they ask you.
Incident angle. So they don't have a diagram.
No.
They don't have a plot.
No diagram. No refractive index. So I also don't know how to do outside.
No. I think maybe because of you miss some information in the question. So what kind of information it is? So what do you mean is a diamond?
They just wrote diamond. The second medium is a diamond.
The second medium is a diamond. The first medium.
I assume it's air and diamond.
The incident angle is this one. So that it
have total internal reflection inside. So they want you to calculate the angle.
They want you to calculate the angle of what?
The critical angle.
This is the incident angle. They want you to calculate the creative angle.
Yeah, so I don't really understand what they're trying to ask.
No, I think you
Maybe I
miss some
email you,
information.
then-
Maybe I think you miss some information. Then I completely don't understand what this question is for. I completely don't. I think maybe you should miss some information.
Then I
Yeah, you can email me
then
so that I
maybe
can.
see the.
Yeah, that I can retrieve your question because currently I don't have access to the quiz question.
Okay.
Only when you email me and then I can ask OAS to send me your quiz paper.
Okay.
Okay. Okay.
Thank you.
Okay, no problem. Okay, so for student team, Daniel, Chuan Wei, do you have any question? Okay. Daniel?